Um, Hi everyone, and welcome to this session. I'm really glad that I can see. Actually, I cannot see anybody, but I can look who is there, and yeah, there is a lot of people over there. So, hi everyone, and thanks for coming and listening to my talk. And today we will be talking about really cool topic. At least for me, I like this topic really well. And today we're going to talk about reactive streams, and especially about the state of reactive streams. Before I'm gonna say anything, I wanna tell you that this is a really smoothie talk, which means that there is no hard stuff. It's really easy to get for everyone. And even if you have no idea what is reactive streams, I will explain all the stuff, and you can learn why it was created, what is the state, and what will be in the future. If you are with me, my name is Oleh Dokuka. I'm really big fan of reactive programming. I am part of Reactive Foundation. I'm a member of technical oversight committee at Reactive Foundation. I'm Java champion. I'm contributor to projects like Project Reactor. If you have never heard about this, this is something similar to RX Java. So I know a little bit about reactive programming, reactive streams. I contributed to some libraries, and I hope that I can tell you a little bit more about reactive and can explain the meaning and the state and the future. So if you like what I'm doing, just follow me at Twitter. I'm welcoming everyone to follow me, and I'm always open to answer all the questions at Twitter direct messages. If you're still with me, let's start. Today we will be talking about the story of reactive streams. We will be talking about the state, and of course we will be talking about the future. Why we need this story? You may wonder why we need to talk about this story, because history is the most important to understand how that happened, why that happened, and why we need to use that today, even today. So that's why we start from the very beginning and end with the future. So first word or sentence that I want to say you, it's that reactive is all about interaction. It's how one component talks to the other, how other component reacts to that event or to that interaction, how it processes data, how it change its behaviors, etc., etc. However, if we're gonna look at the history, the first mentioning of word reactive was in the context of the city, in the paper on the development of reactive system, and how the authors who wrote this paper explained reactive in terms of the system is that reactive system is the type of the system which continuously reacts to all the events and change its behavior, like the system behavior appropriately to incoming event, immediately or eventually at least. So you may wonder, what is the difference between non-reactive system? Because like my non-reactive system looks like the same. It get events, and what is different from my and there, right? So in order to understand that, we will have Goose. The Goose is the hero of the story, and we will ask the Goose to explain all the stuff. So you may imagine, Goose is a bird, right? And we ask something to the Goose, and Goose can be imagined as a system, right? Every one of us is a system which reacts to events and change behavior somehow. So we say to Goose, do that, do this. We change the feeder, the position of feeder. There is not enough food and so forth and so on. And Goose, if Goose is not reactive Goose, right, or not reactive system, will ignore everything, or will react to some particular events, which is the most interesting for Goose. Like a bird, what is the bird interested of? Like what is the most of interest for the bird? It's a food, and the Goose just go to feeder, eat the food, and produce good call, right? I will call it poops. Yeah, we all know that they produce good call as well. But anyways, it's good, but it reacts to only a few events. And if we say to Goose as a system that we change the position of feeder, or the feeder will be appeared in at a different time, once this event ignored, which can be important event, but the goose is not interested in that. Once the goose went to the feeder, it will figure out that there is no feeder, and then it's going to be a crash of the system or of the goose. So like to draw the line between reality, we are building systems, we are building applications, microservices nowadays. And if we ignore, for example, the unhealthy hardware or unhealthy hard drive or unhealthy microservices to which we are talking, and we'll continue receiving requests and sending to the same unhealthy service or hardware, we will crash, right? Because we will get an error. In a good case, this error will be propagated to another service and so forth and so on, and this will be a cascade erroring of the whole system, which is not good for our business. Yeah. In contrast, reactive goose, this is a goose or the system which changed its behavior as a reaction to every event which happened. So if the goose heard that the position of feeder or the time of feeder appears has changed, it will take it into account and will be going to the feeder at the different time. Or if we draw the line with reality or real development of distributed system or microservices, this is how we solve the problem of cascading failure. If we know that there is no other service by this address anymore, or this service is unhealthy, we will be going to another one, or we will provide the response with some fallback or default. That's how reactive system works. It changes the behavior appropriately to all the events that come in from the environment. This is really important. Even so, our talk is not about reactive system. I wanted to mention reactive system because during the whole story of reactive programming, we will see how reactive system reflected in reactive programming evolution and reactive streams at the end. So I will mention reactive system at the early stage of our story. But the story of reactive programming started from very, very late time, from 1890s. And you may wonder, well, what happened at this period of time? Because only now we are using this approach like reactive programming, reactive streams. Well, in fact, at this period of time happened that. At this period of time, people started building computers for everyone. And that meant that computer has to provide something to user, something like user interface, right? And big corporates like Macintosh and Microsoft started their competition, and they started building computers for everyone. And the problem that appeared to the developers of that period of time is that, well, how to build responsive UI? Because previously we were building only some math stuff, or we were building some console applications or something that user will never try out, right? And we don't know how to build user interface because we create only procedures and some functions and use some data and that's it, right? So that was a problem. So developers started building something, and at the very first iteration, I will be shown like this. Right, they did the first demonstration, and the user interface that they created was not very responsive. Right, it's lagging, it's so slow, and we don't like such interface. So you may wonder what they did. Well, if the developers, which has no idea how to build user interface, how to communicate with hardware, which rendering something, might build something simple, right? Like data structure, which collects all the incoming events. Of course, I'm using JavaScript here, but you may imagine some old language like C or C++. Of course, it's not all, but you may imagine that was the very beginning of software engineering at 19 and at this period of time. So they created a few functions which upgraded the position or the state of every object. They moved. They created a few functions, and what they did, well, the really straightforward solution. They created a while true loop, right? That's what we can do in order to check whether something is changed in the data structure, right? And they started checking in this while true loop periodically the appearance of new events, and then applying the new events like mouse movement, etc., to different objects that they wanted to move on the screen, right? And in order to keep hardware cool, I mean cool, not hot, but cool, they said, well, maybe we will check or pull the state of the queue or data structure with some periodicity in order to allow other tasks being executed. So let's do that every 300 of miles, and of course that was too not much to make interface responsive, right? So let me check whether I'm there. Okay, everyone can see me still. That's cool. That wasn't so responsive, and well, engineers started thinking maybe we have to decrease the periodicity, like we have to do that more frequently. Well, good idea. It became a little bit better, but still weird because it's lagging. Yeah, we don't like such movement and animations on the screen. And then afterwards, engineers say, well, I will be doing that infinitely without any abuse. 0, this is while true. Of course, the interface became smoother, but well, if you remember the computers of that period of time, single CPU, single thread, and now you created while through loop, which is working all the time. Well, maybe your UI will be smooth, but nothing else will be working, of course. And that was the problem. So let me roll back that because it took a lot of CPU time, and we are running a video stream here nowadays, and think what we can do. And actually, engineers started scraping their heads, and at some period of time, at Microsoft, engineers figured out that they have to change their architecture. And that's funny because Microsoft became the main leader of building user interfaces for that period of time for their Windows operation system. And what they published in 1992 was a new kind of innovation. What they named it is event-driven architecture. But simply what they introduced to user was called later observer pattern. And you all are familiar with that pattern from Big Dunk of Ford, of course, from their book. And applying this pattern and making your architecture event-driven was a game changer, actually. So let's check that we are still slow here. It's lagging, right? And now I'm changing from pull UI architecture to push UI architecture. So I'm changing how we now render and react to our events. And instead of just pulling the events, we will be reacting to some push notifications or kind of that. And it turned out that now the interface is pretty smooth because we are not checking the data structure. We are being notified exactly at the time of event appearance. So exactly at this period of time, we can immediately apply the change to our data structure. So the UI will get it, catch it, and then render it immediately once that happens. That's why our UI became much smoother, and we started building and we turned into new era of kind of responsive user interfaces with that approach. So Goose approved this approach. This approach looks pretty simple. What you have to do, you have to still use your functions, and then you have to register your function as a handler or observer to some specific observable object, like box, or in our case, it's a window on which we are moving our mouse, etc., etc. Look good. However, there was some but. Yeah, but, not the but. So what happened is basically simple UI started being more complex and complex. And user started asking for complex animation, for complex transformation, smooth UI changes, and so forth and so on. And now in order to build something like this, Goose said, well, maybe it's easy. But in fact, after some period of time, after some work, the Goose figured out that it's not that easy. And the rest of developers agreed, because every developers of that period of time started writing something like this. Yeah, you may say you can read it, but in fact, nah, this is hell. This is pyramid of hell. And once the manager started looking at this code, it said, what the hell is going on? What is the code? And developers say it's my code, it works, but of course others can not figure it out what's going on there. And that was a problem, because once we started building more complex solutions, once we started composing different functions, composing the reaction on different events, and like try to make a composition of them, we started like building something non-trivial, especially when it came to animation. Complex processing were super hard, and as a result, we got super unclean code, and that was a huge problem because nobody can get what's going on in our application, and we cannot maintain it. Fortunately, a few years later, in the same Microsoft, Connell Elliott, with collaboration with Paul Hudak from Yale University, published a paper where they explained their research on improving the code quality, where they provided something called functional reactive animation, or later we will call it functional reactive programming. So what they proposed is basically a really simple solution. They proposed a set of data structures, which is commonly used in order to observe events, to store them somewhere, somehow, and then they provided a set of common functions, because usually we need to do something like zipping in order to combine two events from different sources, or we need to transform it, so maybe we have to create a common function and name it somehow. And they did it. They provided a library which allows, for example, building something complex like this using only 3 lines of code. And of course, this animation is the reaction on the mouse movement with some delay and so forth and so on. And that became super cool. And this technique became super popular in order to build complex animations, complex transformations, combination of different events from different sources and so forth and so on. So that became a solution. Well, let's summarize that period of time, because that was during the 2010 years. So we got observer pattern, and observer pattern solved most of the UI problem, like responsiveness UI problem. Then in order to improve our code quality, in order to improve the programming style and so forth and so on, we created functional reactive animation, and that became a solution, like a solid solution. Looks good. However, there was another but on in the history movement. We turned into the millennium. And you may think, well, what happened at this period of time? If we try to think and remember what happened along with UI evolution in 19th, we will remember that at this same period of time, the network started its evolution. So the problem, another problem that people try to solve is connecting multiple computers into a single network, like doing communication between computers. And by 2000, this became solved. We got TCP protocol, which became like a solid communication protocol. We got HTTP1, as far as I remember, at the same period of time. And now people started building something distributed, right? Before we used only a single hardware. We used only like computer and monitor, and we built all the software within that ecosystem. But now we are getting more and more computational computing problems, and now we need to distribute our communication, computation. We need the databases and so forth and so on. So the problem that appeared at this period of time was how to build efficient communication, responsive communication between computers distributed by network, by location, right? And you may think, well, what can be bad, can be complex here? Let's see. I want to show you another emulation. And now what we're going to do here will be communication between 2 components, right? So let me first show you what I will be showing here. So what we will have at this simulation, first of all, we will have 2 services. The first one, or 2 components. The first one is on the left. The second one is on the right. You may think about those components like a user code or some business logic and the data store, or or database, right? Or it can be in-memory database, whatever. Previously, it was all on the same hardware, all within the same computer and pretty located and coupled with each other, which meant that if it works fast enough, and basically we don't have to think about performance and delay and so forth and so on, because we got used to think that everything was in a single computer. And while it was like that, for example, yeah, what we are trying to do here, we are trying to get 20 elements. Right here, you can see 20 elements. We are filtering the elements because we are saying, give me next, give me next, give me next, because this is like one-by-one approach. And we are getting those elements in order to process them, and for example, in order to display them on the UI, right? So here I have the time of the processing. Here I have the number of processed elements, and here I can speed the velocity of the animation, like moving this thing. So I started. It works. We can see that the database or hardware or in-memory storage returns some elements back, and we can see that it takes around 20 seconds, which is fine, or 20 milliseconds. You may think about any measurement value. Seems good, but it worked in a single computer like that. So once we started building distributed computation, we got call it latency, right? Because everything is distributed. And now in order to send signal, we have to wait while the signal goes in one direction and while the response goes back to us so we can process this response. So now in the communications that we have, we got a new constant, or a kind of constant, which is latency, right? So let's say that latency at 2000 was around 1 second in order to send packet back, forth and back. And if we're gonna look what happened to our communication, we will see that, yeah, let me restart it. Now we have to send a request, which can be a query, right? And now we have to wait for response, request, response. And even if we increase the speed of that animation, we will be waiting for a really long time until we get and collect all the necessary elements. And that's the problem, because now instead of waiting of just 10 smiles, we have to wait a few seconds or even a few minutes, which is a problem. Yeah, nobody will be waiting for that much time. So engineers started thinking, and they figured out, well, if going through the network back and forth is so expensive, maybe we will ask for all the data that the data storage has, right? And bring it back to our computer and store it, and we'll be using from local instead of from remote. That's neat. So they said, well, let's take it all. And I'll show you this animation, this emulation of such approach, and you will see that indeed it will be faster. First of all, it will be faster because you know, the databases is well developed for batch requests, for huge requests, so they can collect everything and send it back. So they collect all the data. It takes some time, of course. Then this batch sending through the network, and once we receive it, we start in processing it. Of course, it takes some time. It takes 7 seconds, but because we have to wait 1 second in one direction, we have to wait some period of time while the data is collecting, and then we have to wait 1 second until we get it back. And only after that, only after this fixed latency, like 2 seconds plus time for collecting all the data, we have to wait and do nothing, which can be acceptable at some level. But anyways, it's good. It was good at this period of time. It was good if the data set was not that big. However, we all remember that that was 2000, and Bill Gates said that 64 megabytes or kilobytes of memory should be enough for everyone. And now we start thinking, well, maybe if we request a few gigabytes or 100 of megabytes at least of data, we won't be able to fit it into the memory of our computer, right? That's true. So another property that a computer has is its memory. A part of that, every network is at 2000 was not super fast, which meant that it had its own throughput, which means that if we are going to deliver a packet of a few hundred of megabytes, most probably the packet or this message will be split into many packets, right? So we have few more other properties in our computer. Like the first one is network throughput, which can be, for example, 23 element, as well as we have memory, which can be some number of elements which we may store. Like let's talk about the number of elements or messages which we can fit into our memory. So first of all, if we again, we got a new element on our screen, which is memory. And once this memory is full, we will see that we ran out of memory. Or if it's not full, then it's fine. So if we request everything from our database and try to feed into our memory, we will see that our computer crash, our application gonna crash because of out of memory. We won't be able to fit everything because computer is limited in size, in like capacity and so forth and so on. On the other hand, we have network throughput, which means that now we cannot deliver all the information at the same time. So first we have to wait until one part of data is delivered, then we have to wait until another part of the data delivered. And of course, only after that we will be able to start processing, which increases the delay between the request and real data processing. In turn, once we will be gathering all the information in memory, we will run out of memory again, which is the same problem. So we have a couple of them, which was a problem, and people tried to solve it. So they started thinking again, and someone proposed, well, if we cannot fit everything at the same time, maybe we will try to split them on batch, on portions. And we will request one portion, process this portion, and request another, process it, and so forth and so on. This is smart. Using batching, we won't have to store everything that database has on their side. We can just store the portion that we can fit into memory, and so forth and so on. So it can be a solution. Let's take a look whether it works or not. So if we're gonna run this emulation, we will see that now we're requesting some number of elements. We know that memory capacity is 23 elements or 25 elements. So we say database give us 25 elements. Database generated, send it back, and then we process it. Once we process, we say, give me another batch or another portion of data. We process it. If we are lucky, then we get it in 2 batches. If we are not lucky, for example, we filtered data and figured out that there is not enough to display on the screen, we will request for another portion. This technique is pretty common nowadays. It's called pagination, right? We all know what is that. And we all know that it works pretty well because we can keep all this information in memory safely. We don't have to face the network throughput because we are sending not that many information to take the whole bandwidth of the network and so forth and so on, which is pretty good solution even nowadays. However, it still takes some time. It's still not super fast because people have to wait, and maybe we have to figure out different solution. So engineers were thinking. Actually, the same problem appeared at Microsoft. Let me just remind you downsides. So pooling is not good because it's not efficient when it comes to network. Network has limit in bandwidth, and hardware has limit in memory. So all these problems appeared at Microsoft. Again, at Microsoft, right? This big giant that we initially didn't like, but it became that Microsoft solved a lot of problems and at its internal. So Eric Meyer with his team started thinking about solution for that problem because Microsoft started moving toward distributed system. Maybe they started building their cloud, which we know nowadays as Azure, who knows? But the problem was how to send data efficiently how to communicate between services in the way that the latency is the minimal, and how to fit all the information in memory. So the team was thinking, and thinking, and then Eric Mayıs said, well, if pooling is not efficient, we already know a solution from the past, from the user interface development, which is push interface, right? Not pooling, but pushing, which means that now, instead of asking for data, we may say, well, this is a query. Please find all the information. While you find this information, please send me chunks of data, for example, through the network, and I will be receiving these chunks, messages, for example, items from the database, rows from the database, and I will be reacting to them immediately, starting processing them, and that's it. And even in that case, I don't have to store everything in memory, which can be a solution. So database is searching asynchronously. I'm receiving data and process them asynchronously, which should be really good. So let's take a look whether this is a good solution. Let's prove whether Eric Mayıs was right. But first, let me check whether I'm live. Yes, I am, which is good. So what Eric Mayıs invented, basically, it's kind of data pushing from one service to another, but then it got a name streaming, because that was the first initial development of data streaming from one service to another. And it turned out that now, first of all, let me restart it. We're requesting information as it was before, so we are sending request or query, but now we don't have to wait until the whole information, the whole data set will be gathered on the database side, right? We can start sending elements once they are found, which is cool, right? The first element can be delivered with a minimal latency, which is around 1 second. On the other hand, since the search is asynchronous, right? We are searching and sending the elements once we found it. It means that we don't have to take the full bandwidth, because once the element is sent, it is being delivered, and then it appears on the client side. It took from the memory, from the network, and bandwidth is kind of the same size all the time, as you can see. On the other hand, we can process elements once they appeared on our end, and we don't have to wait for all of them at the same time, which is pretty efficient. And as you can see, it took 4 miles or 4 seconds, it doesn't matter, for items of time, which is much faster than batching, even faster than give me all, because we have to wait for all the elements. At the same time, we need only 20 elements, which says that we can consume elements and then say, well, we don't need and close the connection, which is cool, which is much more efficient. And as you may see, we don't have to take all the memory, because we are processing elements in ongoing manner, which means that we don't have to keep everything. That's cool. That was a really solution for all the problems. And Eric Mayıs said, well, this is good. Observer pattern is good, but observer pattern, that was what he applied to his solution. But as we remember, observer pattern brings some downside, which is really ugly code. So Eric Mayıs started thinking, well, we have observer pattern. Observer pattern is pretty efficient because we have asynchronous data pushing. But on the other hand, we all know that, for example, if we query some data, we know that there should be the end of the data stream of all the information that we want to take from the database, right? So with observer pattern, it's impossible to get it where is the end. On the other hand, it's unclear how to unsubscribe from this data stream when, for example, we took 20 elements and we don't need more. And that's a problem. On the other hand, we all applied a very well-known pattern, which is iterable pattern or iterator, which has one downside, which is pooling mechanism, and we know that pooling is not efficient. But with iterator, we know where is the end because we have this method hasNext. Plus, we know how to unsubscribe because iterator are usually closable, so we can say close which terminate the data stream or iterator itself. So Eric started thinking with his team again, and he said, well, we have two patterns. What prevents us to combine them? And he said, Eureka. Well, let's apply this approach. Let's combine patterns, and let's use again the solution from the past, which is already there, which is reactive animation. Let's create a set of functions, data structures, which let us process the code cleanly, react to the event, and that's it. So what Eric created got a name reactive extensions. You heard most probably about reactive extensions already. But the main idea which is hidden inside reactive extensions is, again, two patterns, observer and iterator. They kind of close both their downsides, the downsides of each other, and provides some really good solution. So combining these patterns, providing a new set of interfaces like observable, which got a method subscribe in order to say, well, I'm ready to listen to the data. Subscription, which gave an option to cancel the data stream, and observer, which got three methods like onNext, in order to observe data, and onError and onComplete, solved all the problems. And I want to pay your attention a little bit here, and just want to remind you about reactive system. If you look at the past, observer pattern was just a simple one. It was just reacting to events and nothing else, right? It didn't care about other events, about other properties of the system. At the same time, the data sender did not react anyhow to what subscriber or observer can or want to say to it. With reactive extensions, we got few more options. Reactive extension became the first step towards reactive system for streaming. We got this method subscribe, which was an event to say to data stream, to data source, that I'm ready to receive data. At the same time, we got subscription, which gave an option to cancel data stream and notify data producer about the fact that I don't want to receive any more data, which is much better. Can you see it? That's cool. So if we're going to summarize, we got asynchronous data pushing with that technique. We got, with applying iterator pattern, we got the ability to observe the end of the stream, whether it's error or incomplete. And we got an option to unsubscribe from the stream. It's awesome. Even more, this created a really cool TSL. Along with just these three interfaces, reactive extensions provide us with really cool DSL. And I just want to tell you that all these animations, all this kind of visualization and emulation that you have seen during this session were done using RX for JavaScript. And you may imagine how much time you would spend building and composing different observables and like observers with each other in order to build like a pipeline which run this animation. But with reactive extension, reactive programming, I can build it easily because I have a set of operators, of functions, of built-in data structures, which allows me to declare different behaviors, which every element in the stream will have to go through. And that's how my animation runs. And as you can see, this is just 50 lines of code using reactive programming in order to build this complex transformation, reactions to different events, and so forth and so on. And that's cool. I like it. Even more, such an approach became so popular that we got implementation of reactive extensions in different languages, like JavaScript. We got it in Java from Ben Christensen from Netflix. We got it in Swift and many other languages. And the most coolest is that we got the same programming language, the same set of operators like map, flat map, filter. And once you became a master of reactive programming in one language, you can easily use the same paradigm and the same programming approach in the other, which is awesome. So if we summarize what happened we will see that basically reactive extensions solve the problem of efficiency of data sending, the development of complex pipelines, data transformation, data processing pipes became super easy because now we have a set of operators which allows us to do that asynchronously and so forth and so on. And our code became clean with functional reactive programming. Sound good, sound like we are done, but in fact, we got a few other problems. So you may wonder what happened. Basically, let me show you to that. First of all, the problems that we got was related to memory, and we just saw only a single case of data processing, the case where we have fast subscriber and somewhat slow producer. So what we have at the consumer side is processing time, which is 30, and we have twice slower producer. But what if our consumer is way slower than producer? Let's see. The same animation, and now we see that we have to store elements in memory because processing time increased comparing to producing time. And now producer sends too much data, and we are not able to consume all of them, which is a problem because we are ran out of memory again. So engineers started thinking again, because the problem was, well, slow subscriber can easily overwhelm by fast producer, which led to the crash of the system. And on the other hand, the same problem with the same programming language was somewhat a problem, because in JavaScript, one function, for example, flat map, might work in one way, whilst in like concurrent programming languages like Java, flat map may behave in totally different way, because nothing is standardized in the different implementation. There is no specification, right? So folks started thinking, folks from different corporations like Microsoft, Netflix, Lightband, and others, Pivotal, started thinking about that problem, about this ability to control the flow of data, this ability to combine different implementations, and so forth and so on. And they figured out that maybe they have to create a standard. And that standard got the name reactive streams. So what basically reactive streams? Reactive streams is a kind of, again, combination of patterns that we already invented. So what folks did, basically, they took reactive extensions approach and interfaces from reactive extensions, combined with batch approach, because we remember that when it came to receiving all the data stream, in order to avoid out of memory problem, we started consuming data by batches, right? So what they did, they combined this data pushing plus asynchronous data pooling in the way of batching, and they got reactive streams. So they got three interfaces, like publisher, which is the same as observable, subscriber, which got one more new method, which is onSubscribe, as you can see it here. Yeah, we got onSubscribe, and through onSubscribe, publisher started sending subscription, which request method, which is basically implementation of asynchronous batching. Again, mentioning you, just want to pay your attention that, again, the next step toward reactive system, because now we got more collaboration between data producer and data consumer side. Now publisher sends its subscription through method onSubscribe in order to let subscriber control the data flow. It goes even more toward reactive system, right? Even more control and even more reaction to different events. And actually that solved the problem. We got the same efficient push model, we got asynchronous pull batching, and we got three standard interfaces. In order to prove that that became really good solution, let me just show you another demonstration. So what I want to do here is applying reactive streams. Reactive streams works pretty the same as just streaming, but the difference is now that once we send a request, once we request data, we specify how much data do we want to receive, or how many elements are we ready to receive. And since we know that we are ready to fill into the memory 25 elements, we say, give me 25 elements. We received those 25 elements, we process them, and now, just in case we know in advance that everything is asynchronous, we know we can calculate and apply some math in order to calculate latency plus data search on the database side. And you may say, well, we consume data with that speed, so maybe once we process half of the data set, we can request a little bit more in order to have more data once we end up with the previous data set. So using this approach, we can continuously process data, request more, and the whole communication will be kind of asynchronous and streaming-like. And even if we roll back our constants and our processing time to 30, so we have fast consumer and fast producer, we will see that communication will be the same efficient. But what we are going to do, we will be just more frequently requesting for more and more data. And as you can see, the data processing time is the same. So it became a solution, and reactive streams nowadays are one of the most popular approaches for data processing, preserving the stability of the system. There is implementation and there is a specification for different languages. So there is a spec for C# and there is implementation in this ecosystem for JavaScript, for Java. There is like a lot of different implementations in different ecosystems, and the most important, they all are standardized, which is cool. Even more, for Java folks, we have this standard in JDK 9. So starting from Java 9, we have all these interfaces as a part of standard library, which is super cool. So looks good, sounds like we solved most of the problem. We got stability applying push-pull communication approach, but is it the end of the story, right? No, it's not. We have a few other problems. And the next problem is hidden in ourselves, in developers. Because we are developers, right? We like new features. We want to try new stuff. And once it comes to solving common problems and applying and using something complex, we don't want to do anything. Because in fact, reactive streams is a good approach for data processing, for synchronous data processing. But unfortunately, it's really complex. And if it seems that it's easy, like applying map, take, flat map, it becomes really hard when you have to upload another flat map and then another flat map. And then after some time, you get an error, and that's like a shoot in the leg because you have no idea where this error came from. So this became a problem, and engineers started thinking that maybe we have to go back to imperative, right? Well, you may say imperative looks like to be dead for network communication. Well, not really. Long life imperative. Over the time, Microsoft started developing another approach, which got the name async await. So you may heard or you may never heard about this approach, but the idea is to keep your code imperative and simple, straightforward, but work as asynchronous non-blocking. So we may look at this example. We have a remote call to our toaster, and we say, let's wait for a toast. So previously it was blocking, inefficient, but now applying a magic word await, you don't have to block your system, you don't have to block your thread. Everything magically decompile into observer pattern and works as observer pattern, as even though your code looks like imperative one. This approach became so popular that in 2010, one of the fans of reactive extensions said, well, is observable not dead? And the developers said, well, not really. We are developing RX. However, we created a replacement for RX, which got a name async enumerable. So you may think, well, what is async enumerable? In general, async enumerable is an approach for asynchronous data streaming through iterator pattern plus async await keywords. In general, the idea looks like the following. You got like a normal data structure, a normal iterator. You iterate it using normal while loop, but now you add one magic word, which is await. So you await for the next events or sequence of events. And once you got a new sequence of events, you just process them until you got to the end, which means that, well, there is no other events came in. And once that happened, you await again. And once a new sequence appeared, you process it again, and so forth and so on, which is a really working asynchronous data processing, which can be a streaming, but shown as imperative code. Developers like it because it's much easier than asynchronous, which is functional. And the most like important thing I would say, or not good for reactive programmers and reactive streams fans think, is that this approach became popular in other implementations, like JavaScript, like Kotlin, and even in Java, because shortly we will have Project Loom, which is going to bring fibers continuation, which is basically the same as async await, but a little bit different. It will resolve the problem of blocking communication and maybe provide a way to consume stream over iterator. Well, that can be a problem. So you may wonder, what is the future of reactive stream then? Because it's not that shiny for reactive and functional anymore. Well, we have to look at other features that is coming. And one of them is GraalVM. So if you have never heard about GraalVM, GraalVM is two things. It's basically an umbrella over a set of features. The first one is just-in-time compiler, which improves runtime capability of our code, which optimizes it really good. And the other one is TruffleVM, which basically can be explained like this. The idea is simple. You have Java, you have JVM, and you can run basically every language on top of JVM really easy, which means that now using GraalVM, you can run Python, you can run Ruby, you can run JS, C#, whatever within the same JVM. And they all will be able to communicate with each other. So Python can call Java, can call JavaScript and Ruby. And yeah, this is not a fake. I can show it to you. Look at that. So what I have here, I have JavaScript. Yeah. Well, let me continue a little bit more. I'll explain you a little bit more. So the question is, well, how can it work together? Because if we have async await, if we have Project Loom, which is running in the same ecosystem, for example, C# is async await, and JS is async await, and Java is their implementation of async await mechanism. And the question is how they gonna communicate with each other, for example, within the Graal. Of course, every JVM, every language specification has own kind of spec for state machine for async await behaviors and so forth and so on. But there is no like general specification for them. There is no specification for data streaming. And now the question, how your async await function will be called from the different ecosystem? That's a good question. And the answer, I don't know, because there is no spec. However, we have another standard, right? We remember the reactive streams is a standard, this is specification. And Java architect says that that specification is really good. It's a power. And let me show you that power of the spec. So what I'm gonna do now, I will be calling reactive streams built in JavaScript. Not I want to use just Graal. So I have reactive streams, I have RxJS in JavaScript. So this is pure JavaScript code. And now I'm calling Java through GraalVM API. I'm calling reactive streams, consuming this reactive stream, and process it in JavaScript. So you may imagine the use case that you want to convert your legacy JavaScript code into Java or vice versa. It doesn't matter. There is a task, and now we have to solve it. Well, with reactive streams, we can solve it easily because there is a spec for JavaScript, the same as for Java. And now I'm using totally different library, Project Reactor here, and exposing all the data stream as a publisher here, for example. And yeah, this is real library. And now what I have to do, I have to combine, for example, the jar file from my project, which is here. So you can see it here, test. And now what I'm doing, I'm running this JavaScript file that you just seen. And here we go. I started it. And now I consumed 50 elements. Because if we're going to look at our JavaScript code, we will see that, well, I took 50 elements. And you can believe me, if I change this number, I'm going to recompile it, for example, using like this, and recompile TypeScript code into pure JavaScript. And no worries, this is JavaScript. It will always work even though it got an error. So if you're going to rerun this app, you will see, hey, it works. And it works preserving all the important behaviors. So if we're going to log, in Project Reactor, there is an operator log. If you're going to log and rebuild your JavaScript, so what I'm doing here, I'm logging all the events in my Flux in my Flux stream that I have here. So I rebuild it, and I rerun this app again, and you will see that all the events are logged, and we have proper reactive streams communication. We got this onSubscribe event, we got request because there is the same specification but different implementation in JavaScript and Java, but they have the same standard set of interfaces which can interact with each other. And now you can see that we requested 16 elements and we received them. Another 16 received, and so forth and so on, which means now we can easily combine using the same standard set of interfaces, the same specification, absolutely two different ecosystems, and made them working, which is super cool, which is awesome. I like it. But you may wonder, well, two different implementations, two different, like, how often do we need that? That's true. But, well, we may use it for microservices, for example, because we can build the same reactive streams over the network as a standard network protocol. And we can combine two different systems communicating using the same standard, using the same streaming standard, preserving all the request response and this all set of interfaces, but over the wire as a protocol. And there is such protocol called RSocket, which do it for you. So our reactive streams, RSocket is reactive streams as a protocol. There is different implementations in different languages, but no more words. I just want to show you that it really works. What I want to run right now is, again, Graal server, which run RSocket on the JS side through the Graal, because I can. Why not? So I have this Graal RSocket, which runs RSocket server and receive like request stream. And once the request stream is received, it calls my Java library, which is here, the same library as you've seen here. It calls this method, and we will see all the events that are going to happen and going to run through Java side, through compiled through or sent through JS, and sent through the network to my browser. In turn, I have my UI here, which is RSocket UI. And now if we're going to open the same UI, open console here. So let me just open the console. Yeah, let me show you what is in this file. We have RSocket client in JS, which is calling and connecting to remote server over WebSocket. So this protocol can work on top of TCP, WebSocket, Aaron, whatever, basically. And then request stream, which we have implemented on the server side, and then stored my subscription, because everything is reactive stream. So it stored my subscription in the global space, so we can use this subscription over the console. I've done that just for demonstration. You can request any number of elements, but now what I want to show you is that I can control back pressure, real back pressure as it is in specification. For example, if I say, give me 10 elements, I'll receive 10 elements. And if we're going to look at the logs, we will see that request 10 appeared on the server side appeared and the jar library that we connected through the GRAL to JavaScript file and returned exactly 10 elements. And I can request more, for example, 100, and it will work. So let me quickly run to the end because I'm really running out of time. You may wonder, it's cool, but where is the future? Does it really have a future, reactive streams? The answer is simple. You have to think. You have to remember that not every approach is applicable for you. And the answer for your question, where to apply reactive streams, or maybe it's enough to use a sync await, comes from Goose-Coop. Yeah, I'm joking. This is not Goose-Coop. It's a coop created by Eric Mayer in his paper, which you can find the link to at the very bottom. But this paper and this cube says that in general, your system can be described using a few properties: volume, or number or size of your data that you are sending through one service to another, velocity or latency that you need to achieve between communication, and variety of your data set. So you have constraints in your database, or you have simple key value pair, and you are fine with eventual consistency. So if you don't have big volume of data, if you don't need really high speed of data streaming, if you are kind of stick to normal database, relational database, then maybe a sync await is a proper approach for you. On the other hand, if you need real data streaming, you need to send so many data with the lowest latency, and you are fine with k-value storage, then reactive extensions for you, because they don't have any pull-push mechanism, which is of course complex. This is just simple push mechanism, which allows you to process your data, and that's it. However, if you need something flexible, if at some parts of your system you need this proper flow control, at some part of your system you need low latency, then you can use reactive streams, because reactive streams are really flexible. You can request 10 elements, or you can request long max value and say, just send me everything, and it will behave as reactive extensions. So think about it, choose what you need. Also, Kotlin allows you to combine project reactor and turn project reactor into imperative code. They all friends. The only matter is what is the best approach for you. So the final summary. Reactive evolution started from the very beginning, from the UI and enterprise world. It became a standard, a specification for building reactive system, because now we can build real reactive system and can control so many things using the same spec. And of course, standard is always standard. It works as a network protocol in the same way as a spec or set of interfaces, even though those interfaces in different languages and ecosystems, but it always works, and it's a good approach. However, remember that it's not always applicable for all the cases, and you have to think about it. So use Goose-Coop or Eric Mayer's Scoop in order to understand whether this approach is good for you. That's all from my side. If you want to get all the source code, just follow this link. Follow me at Twitter if you want to ask more questions, and thank you for your attention. So I'm not sure whether I have more time. Do I have more time for a few questions? Anybody, just tell me, because it's 15 more minutes that I had to take from a presentation. So yeah, let me quickly answer the questions which appeared at the chat. So I got one question related to, can you give book advice for reactive streams? So in general, I have one interesting topic from which you can start learning about the idea of reactive programming. I will send you a link shortly in the chat. I have to remember the name of this topic, because I'm a little bit distracted now after the talk, as you can see, but I'll share the link to the book. to the blog post related to which is a good start for getting reactive programming and reactive extensions in general. Yes, the slides, as I said, yeah, let me just quickly share and send you the link to the slides. It's publicly available. Here's the link to slides. You can find it at iCloud and you can use it. Feel free to use anything from that. Also, if you're curious about the source code and the emulation that you've seen during this presentation, the source code is available here. Give me a second. I'll drop you another link for the source code, and you will be able to run it locally, to play around with all the animations that I've been showing on your own, and rehearse all the approaches just in case you need it. Or you can look how reactive extensions and reactive programming can be applied in order to build such a complex emulation for like data streaming, for example. All right. Anything else? Any other questions? Feel free to ask anything. So if there is no other questions, here is my Twitter. I'll just copy paste it again. Feel free to drop me a message at any time. I'm open for not this link, but sorry, Twitter, Oleh, Dokuka, yeah, this one. Feel free to ping me at any time, ask anything. I'm always happy to help anyone in order to get some basic of reactive programming, reactive streams. Feel free on doing that. If you need any help with Project Reactor, reactive streams, if you are using RSocket just in case, don't hesitate to drop me a message. I'm always open. And again, thank you for your attention and have a good end of this conference day, and good luck.